Welcome back to the Deep Dive. Today we're going to dive into some pretty interesting research that really tries to get under the hood of how these top-tier AI models actually work, or maybe how they don't work when things get tough.
Yeah, we're focusing mainly on a key paper that just came out, actually, June 2025 from Apple Machine Learning Research. It's got the pretty provocative title, The Illusion of Thinking.
Ooh, okay. Sounds like they're pulling no punches.
Not really, and we're looking at some related work, too, just to get the full picture.
Right. So what's our goal here? What are we trying to unpack for everyone listening?
Well, our mission is pretty clear, I think. We want to figure out what these papers tell us about what these models, especially these things called large reasoning models or LRMs, what they can actually do, and, just as importantly, where their limits are.
Limits compared to, say, the standard large language models, the LLMs we hear about all the time.
Exactly. How do they stack up? And, crucially, how should we be testing them? How do we evaluate them properly so we aren't, fooled by just surface-level performance?
Yeah, that evaluation piece sounds critical. Why does it matter so much?
Because it really affects how much we can or should trust these AI systems in our daily lives, whether we're using them for work or just information. We'll look at how these researchers really poked and prodded at their abilities and some of the quite surprising weaknesses they uncovered.
Okay, let's get into it then.
Okay.
This distinction you mentioned, standard LLMs versus these LRMs. What's the core difference? What's the whole idea behind LRMs?
So the way the sources describe it, LRMs are basically the next generation, and they're designed specifically to make their internal their sort of workings visible.
Visible? How?
Instead of just spitting out an answer, like many LLMs do, they generate this detailed step-by-step process first. A reasoning trace, they call it. Think of it like showing your work in math class. You see all the steps.
Oh, okay. So you can follow along with their thinking. Whereas standard LLMs often just give you the final result, and how they got there is a bit of a black box.
Precisely. And the hope, the theory behind LRMs is that by forcing them to generate this explicit chain of thought, they'll actually perform better. Especially on tasks needing complex logic, because it kind of mimics how humans might break down a problem.
That makes intuitive sense. Show your work, maybe you'll do better work. But the sources seem pretty quick to challenge that idea, right? Especially with how we currently test these models. What's the big problem highlighted in the illusion of thinking paper?
Yeah, this is where they get quite critical. They argue that our standard evaluation methods, using these public benchmarks like math tests, coding challenges, and mainly just looking at whether the final answer is right or wrong, it's just not good enough. It's deeply insufficient, they say.
Why? What are the main flaws?
Well, they point to two big ones. First, there's the whole data contamination issue.
Right. The models might have already seen the test questions during training.
Exactly. It's a huge problem. These models train on such vast amounts of internet data, it's incredibly hard to be sure they haven't encountered the benchmark problems or stuff very, very similar to them, along with the answers.
So if they ace a test, it might just be memorization, not real reasoning.
Precisely. It proves recall, maybe pattern matching, but not necessarily the ability to solve a genuinely new problem. Like you said, it's testing memory, not skill.
Okay, contamination is one issue. What's the second?
The second issue, even if you could somehow guarantee pristine, unseen test data, is that focusing only on the final answer completely misses the point of LRMs. You ignore their key feature, that reasoning trace. You get zero insight into how they got the answer. Was the logic sound? If the answer was wrong, where'd the thinking go off the rails?
So it keeps the supposedly transparent part hidden, even though the model is trying to show it.
Yeah, it basically treats the LRM like a standard LLM, ignoring the very thing that makes it different.
Okay, so if standard benchmarks are flawed by potential contamination and don't look at the reasoning process, how did the Apple researchers get around this? How did they design their study in the illusion of thinking?
Right. This is a really clever part of their work, I think. They ditched the standard benchmarks altogether. Instead, they built their own custom controllable puzzle environment.
Controllable puzzles.
Yeah. The beauty of this is they are totally novel. The models couldn't have seen them before, and they were designed so the researchers could precisely dial up or down one specific thing, compositional complexity.
Compositional complexity. Can you break that down a bit? What does that mean for these puzzles?
Sure. Think of it like increasing the number of steps needed to solve something, or the number of rules you have to follow simultaneously. In their puzzles, which involve tasks like, say, navigating symbolic mazes or manipulating objects according to layers of rules, they could systematically make the problems harder. By adding more steps in a required sequence or introducing more rules or more items the model had to track. But, and this is key, the type of logic needed stayed the same. They weren't changing the fundamental skill, just the number of times you had to apply it or combine it.
Got it. So more steps, more layers, but the basic task remains consistent. And because the puzzles were new, no contamination risk. How did this setup let them look at the reasoning process itself?
That's the point. Because they controlled the puzzle structure, they could generate tons of unique variations. And they didn't just score the final answer, they captured and analyzed the detailed reasoning traces the LRMs produced for every single puzzle.
So they could actually watch the model think step by step.
Pretty much. They could see the sequence of operations, the deductions it tried, how long its trace was, and they could study exactly how its behavior changed as they cranked up that complexity dial.
That sounds like a much more rigorous way to test them. So the big question, what happened? When they put these advanced LRMs through their paces with these increasingly complex custom puzzles, what did they find?
Well, this is where that title, The Illusion of Thinking, really starts to hit home. One of the major findings was something they called a complete accuracy collapse.
That collapse.
Yeah. As they increased the compositional complexity beyond a certain threshold, the LRM's ability to get the right answer didn't just fade slightly, it plummeted. A sudden, drastic drop in accuracy.
Wow. Not just getting harder, but fundamentally breaking down.
Exactly. It suggests that as the problem gets just a bit more complex compositionally, their whole approach just fails.
That's pretty damning.
Yeah.
You also mentioned something about a counterintuitive scaling limit in their effort. That sounds odd.
It is really odd. You'd think, right, that as a problem gets harder, a model designed to show its work would, well, try harder. Generate a longer, more detailed reasoning trace.
Yeah, that seems logical.
And they saw that initially. As complexity went up a bit, the traces did get longer, the models seemed to be putting in more effort. But here's the weird part. Past a certain point, right around where that accuracy collapse started the effort, measured by the length of the reasoning trace, actually started to decrease.
Decrease, even though the problems were harder.
Yes. Even though they had plenty of capacity or token budget to generate more output, they could have written longer traces, but they didn't.
So it's like they just gave up when things got really tough. They produced shorter reasoning even when they had the space to elaborate.
That's what the data suggests. It's super counterintuitive. It implies there's a point where they don't just fail to solve the complex problem, but they actually become less able to even attempt the necessary complex reasoning path, regardless of the resources available.
That really challenges the idea of them scaling their reasoning effort appropriately. It's not just about accuracy, but about their fundamental process breaking down. Okay, so how did these LRMs compare overall to the standard LLMs when tested in these controlled puzzles across the different complexity levels? Did the reasoning trace help at all?
Yeah, the study found basically 3 different zones of performance, depending on the complexity. And they did compare LRMs against standard LLMs, giving both the same amount of computational resources.
Okay, zone 1, low complexity.
Low complexity. Surprisingly, perhaps the standard LLMs actually did better.
Better, without the reasoning trace.
Yep. It suggests that for simple problems, the whole process of generating that step-by-step trace is maybe just inefficient overhead for the LRM. Getting a direct answer from the standard LLM was quicker and more accurate.
Interesting. So the thinking process actually got in the way for easy tasks.
Right.
What about medium complexity?
That's where the LRMs did shine. In that middle range of difficulty, the explicit reasoning trace seemed to provide a real advantage. It helped the LRM navigate problems that were a bit too tricky for a direct guess, but not so complex that everything fell apart.
Okay, so there's a sweet spot where showing the work helps.
It seems like it. But then, and this brings us back to the collapse in the high complexity zone, both models basically failed.
Well,
Both. Neither the LRMs with their detailed traces nor the standard LLMs could reliably solve the really hard problems. It really underscores this fundamental limit that both types of models hit when faced with genuinely complex multi-step reasoning. The trace helps in the middle, but it's no silver bullet for the hardest challenges.
so the LRM approach offers a benefit, but only within a certain window. Beyond the overall collapse, did the researchers identify specific types of failures within the LRM reasoning traces themselves? What was going wrong in the thinking part?
Yes, absolutely. By digging into those traces, they pinpointed some specific weaknesses. A big one was limitations in what they termed exact computation.
Exact computation, like basic math.
Sort of, but broader. It means consistently applying precise algorithms or maintaining perfect accuracy through a sequence of operations. Think step-by-step calculations or running a simulation accurately within the puzzle's rules. They found the models really struggled with this kind of systematic, precise execution.
Hmm. Failing at exact computation sounds like a major roadblock for anything requiring strict logic or procedural steps.
It really is. It suggests their reasoning isn't like a computer program executing an algorithm reliably. It's maybe more like fuzzy pattern matching applied step by step. And that fuzziness breaks down when precision is absolutely required.
Or were there other issues?
Yeah. Related to that, they also found the LRMs reasoned very inconsistently. Even across puzzles that had very similar underlying logical structures, the models wouldn't apply the same approach reliably.
Thus, they couldn't generalize a successful strategy.
It seems not. It points to a lack of robust, generalized problem-solving methods. They might solve one puzzle, but slightly change the details, even if the core logic is the same and their approach falls apart. It's brittle.
The inconsistency feels really important. It again challenges this idea of them thinking in a structured, principled way. It sounds more like sophisticated mimicry that's easily disrupted. How do the other research papers you mentioned earlier fit into this story?
They provide really useful context, showing these aren't just isolated findings. One paper from May 2025 looked at interleaved reasoning. It deals with chain of thought, or COT, which is very similar to the LRM reasoning traces we've been discussing. It basically acknowledges that while COT often helps LLMs reason better, generating these long, detailed traces is computationally expensive. It takes time and resources.
Right, the LRM overhead we talked about earlier.
Exactly. So the interleaved reasoning paper explores ways like using reinforcement learning to make this thinking process more efficient. Maybe by mixing thinking steps with answering steps, trying to get the performance boost without the full cost.
So researchers are actively trying to fix the cost and efficiency issues of these reasoning traces.
Yes, and that ties directly back to the illusion of thinking findings about effort scaling limits. It shows there's this ongoing challenge. The traces can be helpful, but they're costly, and as the Apple paper shows, they don't even guarantee success on hard problems.
Okay, and the other related paper, the GSM symbolic one.
Right, that one's from October 2024. It zooms in on a specific benchmark called GSM-8K.
Yeah, the grade school math problems. That one comes up a lot.
It does, and models have gotten impressively better at it. But the GSM symbolic paper asks a really critical question. Is this improved performance really genuine mathematical reasoning? Or could it be more about the models having seen tons of similar math problems online, basically recognizing patterns rather than truly calculating?
So it questions whether success on the benchmark actually means the model understands math.
Exactly, and that connects directly to the illusion of thinking, finding about struggles with exact computation, and failing to use explicit algorithms. It adds more evidence to this idea that benchmark performance, even when it looks like reasoning, might be masking a lack of deeper, more robust understanding.
So these other papers really reinforce the core message.
Yeah.
The cost of these reasoning processes, the questions around whether benchmark success is genuine, these are big, open questions in the field.
Absolutely. It paints a picture of AI that's impressive in some ways, but hitting some fundamental walls when it comes to complexity, precision, and consistency.
This has been definitely a thought-provoking deep dive, really peeling back the layers on AI reasoning. So let's bring it back to the listener. If you're out there using these models, maybe developing them, or you're just trying to understand where AI is truly at, what's the main takeaway here?
I think the core message really is that we need to be quite critical when we hear claims about AI reasoning or thinking, especially based on benchmark scores alone. High scores, particularly on benchmarks that might be contaminated or only check the final answer, just don't tell the whole story. They don't guarantee robust intelligence, especially for new or really complex situations.
And the reasoning trace idea, while a step towards transparency.
It's helpful, yeah, in that middle complexity zone we talked about. But as the illusion of thinking shows so clearly, it's not a fix-all. It doesn't guarantee the model is using sound logic, being consistent, or can handle increasing difficulty without just collapsing.
That new evaluation method that used the controllable puzzles, analyzing the trace, that seems like a really valuable direction, though, moving beyond just right or wrong answers.
Definitely. It gives us a much clearer window into how these models are trying to operate and, importantly, where they fail. It helps us understand the process, not just the outcome, and maybe pulling it all together, here's something for you to really think about. If even these models, the ones specifically designed to show their work, to externalize their thinking, If even they falter so badly when complexity increases, if they struggle with basic algorithmic precision and consistency, and if they seem to kind of give up when the going gets truly tough, what does that really tell us about the nature of their intelligence right now? Are we seeing genuine reasoning, or is it more like an incredibly sophisticated pattern matching engine that hits a hard computational limit much sooner than we might expect? And maybe more importantly, what does this imply about the path we still need to travel to build AI that can truly reason reliably and intelligently, especially when things get complicated?
A lot to chew on there. Definitely food for thought. Thank you for joining us on this deep dive into the illusion of thinking and the ongoing quest to understand AI reasoning.